recording. That's the first thing. Open up idle if you'd like to follow along. But yeah, the topic for today is bouncing that square around in 2 dimensions. All right, so 2D bouncing, 2-dimensional animation. We're going to make a square, which will be the turtle, right? Bounding box, square, with a random starting position and random starting direction. Ooh. And it's going to bounce off all these walls forever and ever until we stop the program. And it will be beautiful. All right, so that's the goal. And we got started thinking about it last programming lecture. And so we know what we need to do now, right? We talked about how to store what it means to have a 2-dimensional direction, how to move in 2 dimensions. It was, in addition to an x offset, a y offset too. I guess it was just the y offset that we had before when I was bouncing up and down. But now we're going to have an x offset as well. And so that will give us direction. So we're going to have some random direction to start off, and we'll pick that, and it will be an x and y offset, and then the box will start bouncing. And we would like it to bounce off the walls, etc., etc. All right, so that's going to be how it's going to work. That's what it should look like when we run it, right? But here's what we got to do. So we got to draw the screen boundaries as we know how, right? Draw that big box. Then we have to make a square in a random location within those boundaries. And we kind of know how to do that. We were picking a random, at least x direction for the ball when we dropped it. So we can just do the same for a y this time. And then we need to give it a random direction to start in. So we'll have to pick an x offset, pick a y offset randomly. That will be beautiful. And then forever, our loop is going to be try to move, try to scoot in your current direction if you can. Unless something's in the way, right? Move in your current direction if there's nothing in your way. Same as the bouncing ball, but now we have an x-axis as well as a y-axis to worry about. If you hit a wall, bounce off in a nice 2-dimensional way. We talked about how to do that, but it'll make more sense in code, I think. So, yeah, that is going to be essentially the game plan. If we can turn these words into code, we did it. So lower level game plan. So we noticed that we're going to make the turtle our square. So the turtle is going to be the one with coordinates, and we can place him somewhere, which is going to be beautiful. And then the direction is also going to be stored using offsets, right? So the turtle lives somewhere, he has an XY coordinate. And we can store the direction as an X offset and a Y offset, and together that will move you in some arbitrary 2-dimensional direction. X off, Y off. That could be their names, maybe. And yeah, just as easily as you could have gone up and to the right, you could have gone left and up. If you had a negative X offset and still a positive Y offset, that would send you this way. Does that make sense? It's just a bunch of right triangles to pick your direction, all right? So that's up and to the left. Down and to the right would be, if you wanted to store this offset, would be a negative Y offset and a positive X offset. Just a bunch of right triangles at the end of the day, and that's going to give us direction. Any way that we want to move, just essentially draw an arrow and calculate how much do we have to go over on the x-axis and how much do we have to go up on the y-axis. And that will give us all the directions known to man, right? 2-dimensional at least. All right, so yeah, every direction has an associated xy offset. That's beautiful. This looks a bit weird. There you go. And I'll talk about normalization in a second, but I think, yeah, that's good enough to get started. Okay, so let's clean up the code that we had before and make it 2-dimensional. So I copied and pasted. I made a new file called 2dbounce.py just to get ready for the day. And I copied our original up and down bouncing program. So I copied this one. Yeah. This original one that we wrote, just the same speed, constant speed. This is the one that I kept, and so we're going to start from here and go further than that. All right, that's going to be our idea. So most of this is already there, but first we need to change the turtle from a circle into a square. So let's do that. So Python turtle. Is turtle.shape And we had him be a circle and a turtle before, but now we're going to make him a square. So turtle.shape square. And just to make it quicker so that I can test things, I'll say turtle.speed fastest. Why not? We run that. Let's see what happens. Oh shoot, what happened here? Running the code? Did I change him to a circle? Oh darn! I did it down here again. Excuse me. So I guess it doesn't matter what the turtle.shape is up here. I guess we'll keep him a turtle. Maybe that's what it was. The turtle needs to be the square. That's where we did it. That was a bit confusing. Sorry. Oops. Need to close off my string there. And so there we go. Now we have a square bouncing. And now we'd like to give two-dimensional coordinates, right? So I guess let's go back to this, right? So make a square in a random location within the boundaries. Let's do that. Right? So initially, the turtle should start somewhere between, like, what is this? This is what? Negative 200, positive 200, and this is like positive 200, negative 200. So those are like your bounds, x and y between negative 200 and positive 200. Let's do something with that. So let's set the starting location of our turtle. Dun, dun, dun. So we use these variables again, bless you, to keep track of where the square should be and where it should move to. So the turtle x, let's make that a random number between, like, I don't know, negative 150 and positive 150. Why not? And then the y offset, we also want that to be random now. It doesn't just be at the top. We would like it to be anywhere. All right? So how about this? Random.random again for the y, negative 150, positive 150. So this will be, you have to look quickly, but that's where the ball started that time. Started at like the lower right. Started in the middle bottom. And so it's random where it begins now, where it begins its life. Looks like it began its life in the same spot again, but it's supposed to be random. There it was, so he's up and to the right when he started this time. So that's a good start. Next we need a random direction. Okay, so how do we do that? A random direction. Well, remember what a direction is. A direction is just an x offset and a y offset. So we're considering only y offsets right now. Turtle offset was for y only. This was the y offset originally. We also need to introduce an x offset. So turtle x offset. Let's set these both to something. I don't know. The x offset can be 0. The y offset can be negative 2. That's our original bouncing directions. But we'd like these to be random, right? So instead of being 0, negative 2, so always going downwards all the time, let's make it like up and to the right sometimes, up and to the left sometimes, down and to the right sometimes, down and to the left, all right? So that is just pick an offset for both x and y. It can be positive or negative, because sometimes like you want a negative x offset so that you're moving to the left a little bit, as well as in some up and down direction. Or you want a negative y offset so that you move down and somewhere with x, right? So that's going to change where we move, those offsets. So let's get those. And I would like these to not just be whole numbers, because I want a complete range of movement. And so I need to go and consult the random library. I would like floating point. I like numbers with decimal places. So I want random.uniform. Random.uniform, and here's what that gives back. Random uniform between like negative 1 and 1. Those can be our offsets. And so you see how it's going to give me just a random decimal number between negative 1 and 1. And so I can use that for an x offset and for a y offset. Go a little bit in this direction, in this x direction, in this y direction. Random.uniform, negative 1 and 1. Random.uniform, negative 1 and 1. And so those will be our directions. These together, these two variables together will form our direction, all right? And so then we put the turtle in the starting location, and we need to just forever move him in his direction. So increment his x position by his x offset, increment his y position by his y offset, and that'll make him move. All right? So change the turtle's y coordinate by the offset. Also, same for the x coordinate. All right? Turtle x equals offset. This is y plus y offset. I assume I'm going to be changing both of them later. I'm also changing turtle x, which is a global variable. And so I need to declare the fact that I'm doing that way up here. All right, so now in addition to moving in y space, the turtle's y coordinates changing, we're also going to have the turtle's x coordinate change by this offset, by these offsets that we randomly chose. All right, and if I want to deal with, let me comment out, render useless, these bouncing statements. We're not ready for those yet. So if I just make a big string with 3 quotes, it makes it just a huge comment, one big comment, and so this code won't run right now. So let's just move the turtle like this and go to that place. That's all that I'm doing now in this loop. All right. So I picked a random offset for the turtle, x and y. It looks like this, and now if I run it, the x and the y of the turtle is going to change every frame. Watch. Woo, so he's moving down and to the left. Yay. And there's no bouncing right now, no bounds checking. So he just kind of went off the page. But it's going to be random each time. Wait, now he's going up a lot and then slightly to the right. And he flies off into space. Are there any questions about why this is working? Down a little bit. Right a little bit. Flies off into space. Does it make sense why these offsets, positive or negative, are able to affect the position of the turtle like this? Do you see how those are giving us two-dimensional movement? Yay! And so it's random. Every time it'll be a new direction. And that's beautiful. Whee. But I think you might have noticed, right? Sometimes the turtle moves faster than other times now. Right? He's moving a bit faster than the previous run right now. Why is that? You might be wondering. That has to do with an issue called normalization. So if I choose like this direction, right, I could represent this direction with an x offset of like 1 and 1, x offset of 1, y offset of 1. I could also represent that same direction with an x offset of 2 and a y offset of 2. Does that make sense? Same direction, it's just you're moving faster in the x and y each time. Moving faster in the x and y each time. So the idea is, and I guess it's not going to give you 2 ever, but like maybe this is 1 and 1, and maybe this was like 0.5 and 0.5. As long as they're equal, it will still be up and to the right. Same direction, just different speeds. We don't like that. Let's make it no matter what direction we choose, it's always the same speed. So like this arrow is the same length no matter what we pick randomly. Okay. So the solution is going to be, we want to normalize, okay, normalize this offset triangle that we've made so that the hypotenuse of it, which will be the amount that you travel every frame, let's make that 1, all right? So that it's like we're on a circle and like every direction is exactly radius 1. If you choose that direction, you're moving just as fast as if you chose this direction or this direction or this direction. It doesn't matter. The length of our triangles will always be the same, the length of their hypotenuse. Let's force it to be 1, okay? Are there any questions about that? It's kind of like a linear algebra thing. Maybe you haven't taken that class yet. But we're going to make sure that our distance triangle, no matter if we randomly picked it to be like this or like this, that's the same direction. We'd like to force it to always have length 1. Stretch it out. Move it in so that it's always length 1. So keep the same direction. Just make it so that we always move at the same speed. All right, that will be helpful for us. So here's how you do that. It involves the math library, Python math. How do I force the hypotenuse of a triangle to always be 1? Square root. It's going to involve square root. How do you find the hypotenuse of a triangle, first of all? You got to use the Pythagorean theorem, because all we have are x offsets and y offsets, right? So this distance is going to be the square root of x offset squared plus y offset squared. All right, so that's going to be our current hypotenuse. That's the idea. So what we'd like to do is let's normalize. That's the technical term, normalize our direction. It's really a vector. Our direction is a vector right now, if you've taken multidimensional calculus before. Let's normalize our direction so that it has length, has a length 1 hypotenuse. All right. So let's get its current hypotenuse length, right? Direction, hypotenuse length, I guess. That's, I guess I have to include the math library. Import math, because I need square root. That's going to be math dot square root of the x offset squared plus the y offset squared. Plus the y offset squared. Longer statement. Hopefully that makes enough sense. So that's the current length of our hypotenuse. If we like it to be 1 no matter what, we can just divide the x offset and the y offset by its current length. That will force it to be 1 if you try to do the calculation again, right? So let's do that. Let's change the x offset to be whatever it was divided by this length. All right, that'll force it to be length 1 now. Same for the y offset. Let's divide it by that current length of our hypotenuse so that now it becomes 1. Right? Of the hypotenuse is 1. And so now, no matter what direction we pick, we're always going to be moving super fast. Always one unit at a time. So even if you're going that way, just kind of notice in your head how fast it's moving. Even if we're going that way or this way, it's always the same speed now. That length of our hypotenuse kind of determined our speed in whatever direction that we randomly chose. Okay, so we're always moving with the same speed. Any questions about that? It's a slightly technical process, but again, the bulk of the work was just noticing that we needed 2 offsets, 1 for x, 1 for y, and every time we draw a new frame, we want to like nudge the turtle along in both the x and y direction by those x offsets and y offsets. All right, that'll move the turtle in 2-dimensional space, which is beautiful. Any questions about any of that? Because I mean, we're almost done. We just need to bounce them off now. That's going to be the last bit of work to do. All right, so yeah, this is going to involve bounds checking and bouncing. It's going to be very similar to what we were doing down here before. It's just I got to do it for x as well as y. So let's talk about that. So here's our bounding square. There it is. And this is like the center of the screen, right? 0, 0. So let's draw that. Trying to be as accurate as possible. So there's 0, 0. And every one of our, like this bounding square, it's length 400 by height 400. So this is negative 200, positive 200, etc., etc. Like this is this line right here is the x equals negative 200 line. And you can figure out the rest as well, right? So yeah, here's the idea. In this example, the way we're doing it, the turtle is going to hit the left wall when its x-coordinate is less than or equal to, or it tried to like escape the wall, if it's less than or equal to negative 180. It's not exactly negative 200 because you have to consider the width of the turtle itself. So like the turtle has just grazed the wall, it hit the wall perfectly. If his coordinate, remember he's 40 by 40, it's in the middle of him. So there's an offset of 20 to the wall. Do you see that? That's the main issue here. So really, we don't want the turtle to go any more to the left once his x-coordinate gets to be 180, not 200. You see that? Because he's always, his coordinates are in the middle of him. That's the idea, right? We don't want to go any farther than that. So this is the line. We don't want him to pass it in the x-axis. This is the line x equals negative 180, right? So if the turtle tries to exceed those bounds, we want to like rein him back in to just touch the wall, and then we also want to bounce, right? So yeah, hits the left wall when his x-coordinate is less than or equal to negative 180, or he's like beyond it at that point. That could also happen. Same for the right wall, right? For the right wall, if the turtle hits it, that means his x-coordinate was, like if he's just grazing it, he's just touching it, that means his x-coordinate must have been positive 180, right? Because it's always relative to his center. Okay, that's positive 180. X equals positive 180. And I think you can imagine that it's still the same for the top and the bottom. 200 minus turtle width over 2, that really was 180, right? Stuff like that. So similar fact exists for the top and bottom walls. It's always, all right, the turtle has touched the top wall when his coordinate is exactly equal to positive 200 minus half of his width, because his coordinates are centered on him. All right, same for the bottom wall. The turtle has passed or just hit the bottom wall when his y-coordinate is less than or equal to negative 180 again. Okay, so there's a lot going on there. And now the question is, how do we bounce, right? We talked about bouncing last time. If you hit a side wall, you negate your x offset. The y offset stays what it was, all right? If you have the top or the bottom walls, you use the negation of the y offset. Keep the x offset the same. So let me try and prove that to you. Whee. I'll also make a function in a second. But here it is. Here's the bounding square. And here's the turtle. Let me make it a little bit bigger, actually. Bounding square. Here is the turtle. Let's say he just hit this wall and he was coming in, like this was his direction, right? This was his direction this way, which involves an x offset and a y offset, right? So there was an x offset that was negative because that brought him to the left. This was your x offset. It was negative. And then the y offset was positive because it moved him up a little bit. Right? So together they move him up into the left, the right triangle. So when we bounce off, what should the direction be? If we were coming in this way, we better go off this way. So it looks like the arrow should look exactly like this, right? Something like that. I think, yeah, that should be it. That should make enough sense, right? And what is this? So if we're coming this way, we want to bounce off that way, right? What is this arrow? What is this offset? It is, you keep the same amount of going up, right? Keep the same y offset. Go up just the same amount. But instead of going to the left this amount, go to the right this amount in the x direction. All right, so it was whatever you had negated. So your x offset gets changed to be its negative version. And that's the analog of how we were doing the negation of the y offset when we hit the top and bottom row and we had a bouncing ball. Okay, are there any questions about that? That's how you determine your new direction after you hit a wall. You negate, if it's a side wall, you negate your x offset. And if it was a top or bottom wall, you negate your y offset. So watch, that's how this one works. So let's say that we were coming in this direction, and that caused us to hit the bottom wall. We want to bounce off in this direction, right? Which involves swapping the way that we move up or down, right? We were moving down in the y direction. We now want to move up in the y direction, so we're going to negate that, right? But we still want to move to the right in the x direction. Keep that the same. It's just these parts get flipped. Okay? That's the idea. Any questions about that? So that's how we bounce. We know exactly what to look for now. If we ever exceed these bounds, these 180s and negative 180s, and then depending on which wall it was, we're going to negate our x and y offsets. All right? So let's code that up. And then eventually we're going to turn this into a function. So we can do this all over again. So ifs, a bunch of ifs, that's fine. Let's hard code them, just because that's what it was on the slide. So if the turtle's y is less than or equal to negative 180, greater than or equal to positive 180, rein him back in to that. Because he might have tried to go a bit farther than he should have. And so this was the bottom wall. That's when this happens. This was the top wall. That's when that happens. It was too large. So rein the turtle back inside, and then also change the y offset so that we change our direction. So change the y offset so that we move upwards now. Change the y offset so that we move downwards now, regardless of which way we're trying to go with x. So it's the y offset that needs to change. It needs to be the opposite of what it was, the negated form. All right? So that's essentially what we had before. We already dealt with the top and bottom wall. So let's do the same for the side walls. So if, and this is going to involve the turtle's x, right? We hit a sidewall if the turtle's x is too small or it's too big. So if the turtle's x is equal to, less than or equal to negative 180, so we either hit the left wall or we're trying to go past it. I don't know. Move the turtle back inside. So the turtle's x needs to become negative 180 exactly, and we want to change the x offset so that we move to the right now. Okay? Because we were coming at the left wall. The only way we could have hit the left wall is if we were moving to the left. So move in the opposite x direction, which means to the right now. Okay? That's the idea. Same for this one, turtle x. If it's greater than or equal to 180, we either hit the right wall or we're trying to go past it. Move the turtle back inside the wall. So that's the turtle's x becomes positive 180 again, and then change the the x offset so that we move. If we were hitting the right wall, it means we're coming in to the right. We need to move to the left now. So the x offset needs to be its negated form. All right? So if you check all of these, like either you hit the top, the bottom wall, the top wall, the left wall, or the right wall, and if you change the offsets appropriately, the turtle will bounce. Look at that. Isn't that satisfying? So if he ever tries to, like, in the direction that he's moving, exceed the bounds of the wall, if it's ever exactly equal to or a little bit past it, we don't let him go past the wall. We bring him back in if he tried to go past it and alter his course, right? If it's a side wall, we negate the x direction. If it's a top or bottom wall, we negate the y direction, right? All of this. So he's about to hit the left wall, so it's this one right here. We negate the x offset. About to hit the right wall, negate the x offset again. That's what we're checking for. Isn't that so cool? Are there any questions about that? Oh, he's almost getting to the corner. Ooh, darn. And so maybe if you let it play for long enough, he will hit the corner. But this is a good start. Are we good with this? Any questions about what needed to be done to make this work? Ooh, ooh. Oh, that was beautiful. I think that was it. Wow, I'm glad we got to see this. It got recorded too. I don't think that's happened in a previous class. We just got the randomness in our favor today. So, yeah, now he's going to go off in the ether again. So, Okay, that's what happened. And also, we didn't have a chance to show this before, but we cannot use elifs because we might hit a corner. And wow, we did. I had to use a bunch of separate ifs because it's possible at the same time we hit both a top wall and a right wall, or any other combination that is a corner, right? If you hit the corner, that means you hit, right now, the right wall, this particular corner at least. That means you hit the right wall and the top wall at the same time, which means you both need to reverse your X direction and your Y direction. Does that make sense? So like both of these need to fire. So you hit the top wall. This one needs to run. And you also just hit the side wall. You hit the right wall. So this also needs to run. You cannot make them elifs because if it's an elif, only the first one that matches will run. You remember that? So these cannot be chained together. They have to be separate. Technically, I guess you can chain together left or right wall, top and bottom wall, because it won't ever hit both the left and the right wall, or the top and the bottom wall at the same time. But these two chunks of left, right, and top, bottom, those need to be separate because you might hit both of those at the same time. The top and the right, the top and the left, the top and the bottom, the left and the bottom, the right and the bottom. Okay, that's the idea. And so this is working. It's beautiful, but it's making for a very, very long draw frame function, right? I can't even show it to you all at once. It's, all right, move the turtle in its current direction. If we hit a wall, bounce off. That's a lot of if statements. And then actually move the turtle to where we've just determined it needs to be. In that case, I think it would be nice to make another function. Let's make a bounce if hit wall function. Why not? Kind of like how we had it in Scratch, right? Bounce if hit wall. So instead of, like, we'll take all this out of here, make for a very clean draw frame function. We'll just call our function. We'll say bounce if hit wall. Isn't that nice? And we'll have this function deal with bouncing if we hit the wall. So let's call that one. Def bounce if hit wall, and I'll paste all the code that we had from before. And so it's this function now that's checking if we hit the wall and changing stuff. And I think it's going to change X, all of these, potentially. So let's make sure it knows that they're global variables, and they deserve to be changed. And oh no, it looks like there's some indentation issues. 1, 2, 3, 4. Is it happy now? Okay, I think it's good now. So yeah, that's the bouncing. Bounce if hit wall, deal with that up in this function. And so now in draw frame, which we do repeatedly, while true draw frame, it's just, all right, manipulate the X and the Y by the current offset. Maybe that wasn't correct because we just hit a wall, bounce off of it if we did. Okay, and so that changes nothing about our program, it just makes it cleaner. That's a good programming practice. All right. So there's our random direction. It's mostly to the side, a little bit down. You see it kind of moving down a little bit. So slowly but surely it'll hit the corner probably. And we will handle that correctly because we didn't use elifs. Oh, again, left and right. Interesting. That's the power of randomness. All right. So yeah, that was the bulk of the work. Are there any questions about this? If we would like the turtle, the square, to move faster, one thing that we can do is we normalize that hypotenuse to always be of length 1. So we moved 1 unit in his current direction every time. We could multiply that by something if we would like to. We could say, all right, instead of having a hypotenuse always of length 1, let's make the hypotenuse always length like 3. So I'll put a times 3 here. So now the hypotenuse is always length 3. You can check the math if you want to. But now the turtle's going to move a lot faster. Maybe that's what you like. But you can alter that as much as you'd like. All right, it's just the offset. How much do you want to move per frame? If you move faster every frame, you're always being shown at a constant frame rate, most likely. At least the computer is trying to. Then, all right, if you move faster each frame, move more each frame, that means it's a faster animation. Almost at the corner there. All right, so you can change that up as much as you'd like, but I'll keep it at 1. back to how it was. So that's a fun program that we just wrote. Very complicated, but we planned it out and we wrote it together. Bouncing off the walls. Are we good with this one? Because the last thing that I want to talk about today is just getting us set up for the next programming lecture. These programs that we're writing, we need to plan them a lot more than the other ones. So the goal, finally, is we have this ball bouncing, or the square bouncing on the screen. I would also like to show you how to move a rectangle with the keyboard, right? So we can make a paddle. Our goal is going to be to finally recreate Pong in Python. All right, that's where I'm going with all of this. We have the first piece now. We have a ball moving around in 2 dimensions randomly. Now we need to add the paddle, and the paddle needs to be controlled by the keyboard. We haven't really talked about how to control the turtle with the keyboard yet, and so that is the next step. All right? So we need keyboard input if we want to do Pong. Got to make the paddle, right? And here's the idea. You can make the turtle the paddle too. Here's your bounding box. You can just stretch out the turtle a lot in one direction and the other direction. Okay? I've noticed that if you stretch him by 1.5 in the x direction and 6 in the y direction, I think his original size is 20 by 20. And so that would force him to be 30 by 120, and that looks good enough for our programs. Right? So if you stretch the turtle, you can stretch him in by different amounts and different axes. So that's pretty cool. I can show you that probably, if nothing else. We'll get there. So yeah, the goal is to make a paddle on the screen now and have it be controlled by our keyboard, like the up and down arrows. Okay. So let's at least get the turtle looking like a paddle. That'd be cool. I'll make a new file. I don't really want most of this, but let's see. Let's take some of these things. Let's take the top half. I'll call this paddle.py. So, let's see here. Draw our bounding square, make the turtle the square, make the turtle the paddle. Shape square, color pink, sure. And now instead of turtle size 2.2, which would look like this, sure, save it. Instead of size 2.2, let's have the turtle be size, let's stretch him by 3 in the x-axis and 6 in the y-axis. Or sorry, 1.5. 1.5 to make him 30. Oh gosh, I got too many windows open, sorry. 1.5 in the x and 6 in the y. And then he looks like this. Okay, so that's a nice paddle length, I think. And so that's pretty cool. And the width is all off now, but that's a good size for the paddle, I think. Next, we need to put him in a nice place. Maybe we could set his, I don't know. I think the turtle's x, turtle dot up, turtle dot go to, his y should definitely be 0. Put him in the middle of the screen, and then I don't know, negative 180-ish, 175, I'm not sure. Let's play around with where we want him to start. Does that look fine? I don't know. 160. What did I do last time? Let's see. I think I chose 170 last time, so I don't know, that can be our magic number. That seems like a good spot for the paddle to start, right? And now we'd like it to be movable. Movable by our keyboard. If we press a button, the turtle moves. Because the turtle is the paddle right now. He's just a weird looking turtle. Okay? So yeah, that's what's going on here. Turtle size, 1.56. I guess I should say a few things. Instead of hard coding negative 170 and 0, because we're going to change the location of this paddle, let's do the same thing that we were doing with the ball. So paddle x, start that at 0. Negative 170. Paddle y, let's start that at 0. And then turtle.go to paddle x, paddle y. And so we can just keep doing that kind of thing. Those variables will keep track of where we want the paddle to be. All right, that's the idea there. Go to paddle X, paddle Y. So that's the same as before. And now, here's the beauty of key presses. There is a way to get the keyboard in the Turtle library. You can say turtle dot on key press, and you can set up a function to be called whenever your key gets pressed. And you can set up like, I want this thing to happen when the up arrow gets pressed. I want this thing to happen when the down arrow gets pressed. This thing to happen when the space key gets pressed. So it's on key press, and it takes two things, a function and the name of what key you want to set this up for. So you define a function that does something, and you say turtle dot on key press. You give it that function, and like you say as a string like space. And this function called fun will be called whenever the space key gets pressed, which is really cool. All right? So we're going to do kind of like this. We're going to make two functions, one for moving up and moving down. Def, I don't know, go up. Here, let's put this up at the top so you can all see it. Def, go up. Dot, dot, dot. Same with go down. We're going to make two functions like this. And then we're going to set up these functions to be called when we press a certain key. So we use this kind of syntax. All right. We'll say turtle dot on key press when we press, and you can represent the keys with just strings. So the up arrow is capital up, for example. So when we type up, we would like to call the go up function. And that'll happen. Well, we're just setting that up. And then when we type the down key, this will look for the down key. Once that gets pressed, it'll always call this function every time it gets pressed. That's what these do. All right. So this is what we're doing here. We're setting up these functions. Set up functions to run every time the up/down keys are pressed. So every time I press the up key, it'll call the go up function and do whatever I put in there. Whenever I press the down key, it'll call the go down function and it'll do whatever I put in there, which is beautiful. And that might involve moving the turtle. And then finally, at the very end, you have to say turtle.listen for a weird reason. It's like the turtle's not ready to look for these keys until you ask him, like, all right, I've set up everything I want to look for. Now go and look for those. That's what you do. So it's turtle.listen at the very end. It tells the turtle, like, hey, stick your ear out. Listen for me to press these keys, please. Right? And that's the metaphor, I guess. And so, yeah, every time I run this program, it'll start listening for these keys and call these functions whenever I press things. And so, I don't know, if I go up, what do I want to do? I want to change the position of the paddle, right? Here's the paddle. If I press the up arrow, I want the turtle to move in that direction, which involves changing which variable, which axis do I need to move, right? Should I change paddle X or paddle Y when I press the up arrow? Which one would make him go up? What do we think? Y. Good. Yeah, it's just like the bouncing ball. And so I'd like to move the turtle in the positive Y direction every time I press the up key. So I'm setting paddle Y. It's a global variable outside. I have to do this silly thing. But yeah, every time I press the up key, I like to set paddle Y to be what it was, plus 10. Something like that. 10, 20. Play around with whatever you like. And then you have to remember to tell the turtle to actually go there. This is just a variable. Turtle.goTo actually sends the turtle somewhere. So go to whatever the current values of paddle X and paddle Y are. All right? And so a similar thing is going to happen for go down. If I press the down key, I would like to change the paddle's location in the Y direction by a negative amount. And that will move the turtle downwards. Okay? Go to that new place. And that should do it. So here's my paddle, and now I will type the up arrow. Boop. And I just He nudged himself up a little bit. Up, 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 up. And then I can also press down, go down. It'll call the go down function every time and move him by 10 units each time I press the down arrow. Isn't that cool? Boop. And you can hold it in, kind of moves in a certain way. The sad thing right now is, watch what I can do. Oh no. I need to do bounds checking for this paddle just like I was doing for the ball, for the square. I don't want the paddle to ever exceed those bounds, right? Because then he goes out here, woo, bring him back though with up arrows. But we have control over the movement. We want to make sure that the paddle stops at the top wall, stops at the bottom wall, right? That's the idea. So, that is our goal. We need to do that kind of bounds checking. So we used on key press to set up those functions to get called. We said .listen to make sure everything happens. So now we just need to figure out like when is the turtle at the top wall? Like when is he hitting right here, and we want to like rein him back in. Don't let him go any further. Okay. So this we got to check y's, right? So this is the y equals 200 line, and if the turtle hits the top wall, that means his top half of him has just grazed it, and sadly the turtle is relative to his center. What in the world is this amount? So, like, what is this y coordinate is the real question, all right? That's y equals what? Well, if we know that his height is 120, this amount right here is 60, right? So that will tell us what to look for. We want to check for the y equals 140 line. If the turtle has tried to exceed a y value, a y coordinate of 140, given the length that we know he has, that means he's trying to go past it. If he's exactly equal to 140 in the y, that means he's just touched the wall. If he is bigger than that, or trying to be bigger than that, we don't want to let him go that way. Okay? So don't let it get any bigger than 140, and likewise, don't let it get any smaller than negative 140 in the other direction. Okay? So that is the last thing that we need to deal with, and so the go up function needs to be changed, and so does the go down function. We want to go up if we can, go down if we can. All right? If we're at the wall, don't go any farther. So make sure we don't go past the top. And that is, we just discovered it's 140. If our y tries to be over 140, if paddle y is greater than or equal to 140, that means we just hit the wall, or like it's past it. Just rein the turtle back in. Make sure that is exactly equal to 140. That's just touching the wall. All right? Same for go down. We move the turtle a little bit. If we tried to go past the bottom wall, though, past the bottom, and so that's if his y is less than or equal to negative 140, rein him back in to the just touch the bottom wall, make him equal to 140. Okay. I guess technically I could change this to strictly less than, because the equals case doesn't change anything. But that's how we fix that. Does that make sense? So just two if statements. Make sure that you don't go too far. So now, if I press up, I'm pressing up right now, and he cannot go anymore. It's beautiful. Let me hold him down. Whee! And then he stops. Up and down, up and down. All right. So that is the beginnings of Pong. We have the paddle, we have the ball. All that's left is to like hook them together. Isn't that cool? We're almost there. It took a lot more work than Scratch. This is what the Scratch programmers had to make for you, though. They had to implement this kind of animation at this low of a level, so it's so easy for you to do. Okay? But this is the real work that needs to be done by somebody, and now we're doing it. All right. So, any questions about anything that we talked about today? So that was 2D balancing. All right. Let's see what we got. Dun dun dun. We talked about the test. I think, yeah, that was everything that I wanted to talk about today.